Sudweeks, going to talk to us today. This will be very interesting.
I appreciate this opportunity to share with you some ideas. I'm going to be talking specifically about causal inferences in peer review. I'm suggesting that in a time when people want evidence that schools make a difference, including colleges and universities, they pile huge amounts of money into schools, universities. So do you. You put not only large amounts of money, but you put huge amounts of your life in terms of time, days, months, years, in terms of getting an education. You have a right to expect that it will be in effect. So even nowadays, accrediting agencies want universities to specify the learning outcomes that they intend to achieve, and then they want evidence that those are being produced. Policymakers also ask other kinds of questions, like the four that I've proposed here. We have an effort nationwide to prepare students who come from homes that may be disadvantaged in terms of educational preparation. So we have programs like Head Start that are supposed to bring those kids up to speed. Well, the question is, does Head Start make a difference? Is all that money producing some result? And then there's some other questions there about reducing average class sizes in grades 1, 2, and 3. Does that affect students' achievement in math? Our legislature keeps asking that question. What effect does participation in summer reading programs have? We had a student a year ago who did a dissertation on that topic. And what if we retain children in grade and do not allow them to be advanced, what we used to think of as promotion? Does that have an effect on their subsequent achievement and also on their social emotional development? Well, those are questions that not only policymakers ask, but stakeholders like parents and you and I sometimes ask those kind of questions. So as a result, researchers and evaluators are often asked to design and conduct formal studies to investigate those kind of questions. Please note that either implicitly or explicitly, those questions involve concerns about causality and causal inferences. Now, I dared to use that C word, cause. Researchers often are very shy about using that word cause, and so they make up euphemisms to avoid using the word cause. They use others. Well, usually it's not possible to prove a causal relationship or to provide conclusive answers to those kind of questions. Nevertheless, it is possible to formulate credible causal inferences based on carefully designed studies and appropriate analytical procedures. And that's what I want to talk about today. I just mentioned that often researchers and evaluators are shy about making causal claims, so they couch their language so that the causal claims that they do make are set forth in implicit rather than explicit terms. For example, they say, well, X makes a difference on some outcome variable Y. Or it brings about. Or it leads to. Those are euphemisms. And it's self-deceptive if you're not careful what you're doing there. But people ask causal questions. Psychologists ask them, especially clinicians, counselors, developmental psychologists. Sociologists and criminologists do, economists and econometricians do, and educational researchers often do, especially evaluators in various disciplines. And especially people in the medical and sciences. I've been reading a book lately that I'm only partway through. I recommend it if you're interested in this topic. It's called The Ghost Map. It's a very interesting story about the research of one man in England 150 years ago trying to find out what caused cholera. That disease was widespread and it was wiping out large segments of their population. So this man did some cause and effect research. Well, you can see funding agencies also ask questions about cause and effect. Now, it is often difficult, as I mentioned a few minutes ago, to provide conclusive answers, but it is possible, especially today, to at least make defensible causal inferences based on evidence. There are three important lines of scholarly inquiry that are converging here. By the way, there is a handout of these slides. There are only about 10 of them here, but some others are coming in a few minutes. If you want one, you can take a copy of that. And there'll be some more here in a minute. Please notice the work of Donald Campbell in psychology. Started back in the 1950s. He died about 1999. He spent 45 years of his professional career focused largely on these kind of issues. Then the work of Donald Rubin, who started in was a graduate student in Harvard in the late 60s, but his real work on this began in the 70s. He got introduced to it because he was asked to deal with the question, does cigarette smoking cause lung cancer? Not an easy question to answer, but over the years made some very important contributions there. And at the same time, the work of James Heckman down here from econometrics. Well, those three different lines of inquiry have converged in a very important way that supplements and complements each other and provides us with some real guidance here. So now just a little bit about Campbell's work. As he points out here, he developed and progressively refined a typology for anticipating threats to validity of causal inferences. Identified about, if I remember right, about 46 different kinds that he classified into 4 categories: internal validity, external validity, statistical conclusion validity, and construct validity. Just pass them around back there. Well, these are reasons why we might be suspicious of a causal claim. There are alternative explanations that might account for why the apparent causal relationship exists. Over a period of time, Campbell, he started out with only 2 of those categories, then he added a 3rd category, added a whole new category in the 90s. This has made a very important contribution to the way we think of these kind of studies. He also cataloged a broad range of designs and described their susceptibility to the different kinds of threats. Then he later repented of this idea of trying to say that such and such a design will always work, it'll always solve these problems because it's immune to these threats. And in the latest publication in 2002, which was published after his death, that's this book right here, he focuses less on the designs and more on the design elements, the structural features that can be applied by a knowledgeable person who uses them as tools by anticipating the threats and then asking, what can I do to reduce their plausibility? So this is a very valuable work. So that's, in a sense, that's a way of summarizing his 45 years of work.
What's the name of Campbell's book that you just showed?
This one is called Experimental and Quasi-Experimental Designs for Generalized Causal Inference, and it's going to be, it'll be in the bibliography that I'm going to give you. By the way, Campbell's 45 years contribution here started with a journal article in 1957. Then later, with the help of Julian Stanley, they published a chapter in this book called Quasi-Experimental Designs for Research on Teaching. This is the Handbook of Research on Teaching. That one chapter became so popular and so widely cited that within 3 years, the publisher of this book, Rand McNally, republished that chapter as a book by itself, and they took off for teaching at the end because it applies to designs in all kinds of social sciences. But that developed into a full book in 1979, and then this third edition is really the culminating one, and Campbell had died in the meantime. But notice here that Donald Rubin also made contributions. His main one is this refinement and elaboration of the counterfactual framework, and I'm going to go into that in some detail in a few minutes. Notice that it was originally proposed by the scholar, or the philosopher David Hume, a Scottish philosopher back in the 18th century. Then further developed by a Polish American by the name of Jerzy Neyman, a statistician. But Rubin is the one who really refined it for use in these kind of situations. And he also proposed propensity score matching, which we'll talk about in a few minutes. Now, for centuries, philosophers and other scholars have debated the whole question of what is a cause, what do we mean by an effect, and what constitutes credible evidence that some program or treatment has caused an intended effect. Well, the counterfactual framework provides us with a way of addressing those kind of questions. So I want to spend some time here. This framework provides a useful basis for defining what an effect is. It also provides a basis for defining what counts as evidence of an effect, and distinguishing between different kinds of effects. So I'll talk mainly about 2 different kinds of effects, but there's a half a dozen others, well, 4 others. And then it also provides a basis for designing studies that can lead to defensible causal claims. Even though we can't conclusively prove them, at least we can support them and make them defensible with an argument and supporting evidence. Well, I'm going to skip over this one. And I'm not going to spend a lot of time on this one. There's a very important book that'll be in the bibliography that I'll give you on counterfactuals and causal inference by Morgan and Winship. That's the one that I'm referring to here. So here's the primary question: what is a counterfactual? Well, please note the description here. It's an event, a condition, or situation that is contrary to what actually happened. So one purpose of a causal comparative study is to observe what did happen to people when they were exposed to some kind of a treatment or innovation or new program. The counterfactual is an attempt to describe what would have happened to those same people if they had not experienced the treatment. So what's an effect? Well, it's simply the difference between what actually happened and what would have happened if they had not been exposed. Now, if you're thinking carefully, you will note there's a basic problem here. We cannot, at least we haven't learned how yet, to simultaneously expose people to like a blended learning treatment and measure what did happen, and then ask what would have happened to the same people if they hadn't. We can't directly measure that.
2 dimensions.
But it is a counterfactual. we can still posit that, trying to find an estimate of it. I'm going to skip this one too. So here, consider an example of a possible study. Suppose that we have data for a causal comparative study that includes N persons. We'll say N one of them were in the treatment group and N sub naught of them were in the control group. Now, I'm going to give you a possible example. Suppose, for example, that we wanted to know, does it make a difference on people's GRE scores if they spend several hundred dollars, I'm not sure what it currently costs, plus a lot of time to take what's called a GRE prep course. You know, they're offered all over the country, right here in River City. But they cost money and they cost time, with the promise that they'll make a difference, that you're going to score higher on the GRE as a result. Well, does that really make a difference? That's a cause and effect question. And it's an important one. Well, I'm going to show you a layout of the data. Note that the data set will include a column designated each participant's treatment status. We'll say D equals 1 if they're in the treatment group, if they participated in the GRE prep course. And we'll assign them a 0 if they're in the control group who didn't participate in it. So here I've got all the people listed. We've got down to here N1. So every row up there is in the treatment group and every row down here is in the control group. And we've got a score over here for each one of them. And it looks like, on the average, the scores in one group are greater than they are in the other. So maybe there's an effect. Well, Rubin says this. He says each participant has 2 potential outcomes. This is we're using the letter Y to represent the dependent variable. In this case, it would be scores on the GRE test after treatment, if you've been in it. And down here would be the value of the score if you had been assigned to the control group. You're still going to have a GRE score. Okay? So those are 2 potential outcomes that every person has. But we can never measure both of them directly. We can observe Y1 for people in the control group, but not Y0, pardon me, for people in the treatment group, and it would be just the reverse for those in the control group. But even though we can't measure them directly, we can still imagine the possibility that individuals in both groups have both kinds of outcomes. So here's our data layout again. We've got scores for people in the treatment group. We've got scores for people in the control group. Notice these are actual scores. These are potential scores, so this is a counterfactual, and this is a counterfactual down here, counterfactual condition.
Richard,
Yeah,
how do you come up with those? Are you coming up with actual?
listen up.
All right.
Oh, how did I get these numbers?
Yes. How do you come up with the counterfactuals themselves? Are you extrapolating those from?
Well, they're never observed, right? Like ever.
Depends on which design you use.
Okay.
So we'll come to, hold on.
All right.
So I've already talked about that. Now look, if we could measure both for every person, both the score they would have obtained if they'd been treated, that would be this one, and the score they did get if they were treated, then we just subtract those 2, or subtract this one from that one, and that becomes a measure of effect. We're going to call that the individual treatment effect. But since this one over here is counterfactual for that group, we can never measure that directly. and we couldn't do it for the other one either, but we can still define what we mean by an effect here. An individual effect. Now, the answer to the question Peter asked was, you can't answer that for each individual. But, so this whole column over here are counterfactuals. We can define them, but we can't measure them directly. Can't observe them. But we can compute a statistic that is conceptually equivalent to the average of those individual differences. So if we can call this the average treatment effect, it's equivalent to the sum of all the individual effects divided by the number of people in the control group and the number of people in the treatment group. So this gives us an estimate, Peter. Gives us an estimate of the overall effect, the average effect. Now, let's talk for a minute about what we mean by the expected value of a statistic. It's the value of the treatment group mean that would be obtained by administering the treatment many times to a different sample of participants each time. If we did this, the mean would vary from one implementation of the treatment to the next. But by computing the average of all the resulting means, we would have the mean of the means. This long-run average across replicated samples is called the expected value and is symbolized by expected value of what? In other words, the expected value of the dependent variable in the long run. So, back to that chart we had a few minutes ago, I've now collapsed the rows, and so I've said here's the mean of the people who received the treatment, and here's the mean they would have received had they, this is the mean of the counterfactual mean. That's what they would have received had they had been exposed to the treatment. Down here's the mean of the control group, that's factual. Here's the mean they would have received if they had received the treatment. So, the average treatment effect is simply this distance, this right here, minus this right here. Now notice what we've done. According to this reasoning, we have actually used this mean of the control group right here as a proxy, as a substitute. We've used it to estimate what the mean of those people would have been if they had not received the treatment. You with me? That's the counterfactual mean right there. We use this as an estimate of that. And the difference between them, see this one is right down here, this one is up here, those are two factual groups. The difference between those is what we call the average treatment effect. Now that's one estimate of the causal effect too. Now, please note, I'm going to talk for a minute about random assignment and treatment status. When random assignment is correctly implemented, the potential outcomes, according to Rubin, are independent of the treatment status. So whether you get a Y here or Y0 there, that's independent. And that little symbol right there, that upside down T, symbolizes statistical independence. There's no correlation between group membership and that outcome. So, the two expected value terms are exchangeable. Consequently, one can be substituted in place of the other, can be used as that proxy that I showed you just a minute ago. So when that condition is true, there's no bias. It's equal to 0. When that condition is true. Now, I mentioned one possible treatment effect up here is called the average treatment effect. There's another one called the average treatment effect on the treated. Those two are identical if you have random assignment that truly worked. But in most cases, they're not identical. Because here's the one, the average treatment effect, here's the other, and you have this troublesome term over here. If random assignment is really working, that term falls out and becomes 0, and those two are equivalent. But in the practical world, this is usually a non-zero term. There's selection bias. Everything that Campbell has proposed, everything that Rubin has proposed, is an attempt to minimize that term or to make it go away. In the real world, we usually don't make it go away unless random assignment really works. So when random assignment is correctly implemented, the bias is 0 and drops out of the equation. And those two effect estimators down here are equal. So, bias is eliminated, and this elegant result is the reason why experiments are often viewed as the gold standard for conducting research to investigate cause and effect relationships. The problem is, they're not always feasible. Or, even when they are feasible, they're not always correctly implemented. Or even if you implement them correctly, you end up with a lot of dropouts. You have an attrition problem. So, what I call the average treatment effect right there is that difference between those two, but we use this one down here to substitute for it as a proxy. Now, selection bias is the difference between which ones? It's the difference between this one up here. Am I saying that right? No, it's the difference between y0 and 1 is the difference between that one and this one, the two counterfactuals. I said it wrong, here it is. So here's the summary. That's the average treatment effect, the comparison of those two. This is the average treatment effect on the tree. And the difference between those two on the right is the bias term. That goes away if you have true random assignment. So then you can use this one in lieu of that as a substitute. This is the counterfactual model that Rubin has proposed and has become widely used in the last 25 years. But I want you to remember that those two are not the same except in a truly randomized experiment. Otherwise, they answer different questions. They're both useful, they're both important, but we wouldn't want to confuse the two. Now, we've talked about random assignment. I want to emphasize what it does do and what it does not do. When it's correctly implemented, the resulting groups will be equivalent in expectation. Consequently, the random process increases the probability that any differences between the groups on both observable and unobservable variables will be smaller than what you would expect due to sampling error. So if you did a hypothesis test, you would find that it wouldn't be significant. In other words, random assignment minimizes the likelihood of threats to validity, to causal inferences, due to differences between the groups prior to the treatment, or if the treatment hadn't happened. But what it does not do, it does not guarantee that the resulting groups will be identical prior to the treatment. It says they will be equal in expectation. In the long run, they will be equal, but not in any given instance. Now, here's some important limitations of random assignment. You can't legally or ethically manipulate people sometimes. You can't. I should tell you a brief experience. When I was just finishing graduate school, I was asked to work for the church education system as the director of research and evaluation. One day my boss called me in and he said, "Rich, you got to help me." He's asking again. He keeps on asking me. He calls me every week as if I knew who he was. Well, it was the general authority who was calling the man who was the administrator of the church seminary program. He said, he calls me every week and he said, we should stop having early morning seminary. We should cease doing it because it's causing students to not do well in high school. He had a granddaughter in Hawaii who was in early morning seminary, and she was failing in high school. And he was convinced, this was a general authority, that we should do away with early morning seminary. And he'd been on my boss's case for months. And so my boss said to me, you got to do something about this. We got to find out. If it's true, we need to know. And if it's not true, he needs to know. So, design a study where we can find out. I was just out of graduate school. I said, sure. We'll randomly assign half the kids to go to early morning seminary and half of them not to. Well, he wasn't very thrilled with that. So he said, find another way to do it. Well, we eventually did. Because in order to prove causation, you have to at least have a correlation. There has to be some other conditions met too. But if you don't have a correlation between grades in school and participation in seminary, then there's no causal relationship. So we collected grades from a lot of schools in California, in high school, and we made a record of their participation in seminary over the last 4 years. And we found the correlation between the two was essentially zero. You don't have to worry about a causal effect if they're not related. Now, correlation doesn't cause, it's not evidence of causal effect. But the absence of correlation is the evidence of the absence of a causal effect. My boss, whew. I'm not going to tell you who that general authority was, but he later became president of the church. We still have a seminary system. But you can't do that. You can't randomly assign people to go to kindergarten or not. You can't randomly assign people to take a mathematical remediation course in algebra if they're not prepared when they get to college. But policymakers still want to know. They spend all this money. Our own legislature keeps claiming that we're spending all this time, all this money at UVU and Salt Lake Community College to re-educate students and freshman students who aren't, they don't have the math skills to take college algebra. You know what? BYU does the same thing. So people want to know that when they take that course, does it make a difference? That's a causal question. There have been a few studies designed to do it. But you can't do it using random assignment. So even if it is possible, it may not be desirable. And it doesn't work very well with small samples. And even when it does, when you can use it, you have some parents who say, you're not going to send my kid to the control group. Or they say, nothing doing, my kid's not going to be in that treatment group. So all those are reasons why you can't do it. So do you throw up your hands? Do you say, I can't answer that question? Or do you proceed and do the best you can? Well, if Campbell were here, he would say, that's why we have quasi-experiments. If Ruben were here, he'd say, that's the whole purpose of my work. By the way, what does the word quasi mean? Say that louder, Peter.
Almost.
Almost. So a quasi-experiment is simply a near experiment, an approximation, a close to experiment. Some of them are much better than others. You have trouble implementing randomization, you have trouble implementing quasi-experiments too. This is taken from a paper by Rubin in 2008. He says all statistical studies for causal effects are seeking the same type of answer. And real-world randomized experiments and comparative observational studies do not form a dichotomy. There is no black and white line up here where on one side they do and on one side they don't. Rather, it's a continuum. Good quasi-experiments are close to this end over here. But there are some not so good quasi-experiments that are over here and over here. So it's really a continuum rather than a dichotomy. And random assignment is not the only wheel in town. One alternative, for example, is to use propensity score matching. I'll talk about some others, and well, here they are. This one was proposed by Campbell clear back in the 1950s. This one is proposed by Rubin about 20 years ago. The econometricians have proposed this one. Here's a Campbell one, and there's a whole lot of other possibilities that Campbell and Rubin have proposed. These are some of the best. These would be on that right-hand side of that continuum a minute ago, these up here. These two here would be farthest to the right, these two here would be next, and these here would be farther to the left. Now, in the limited amount of time, I can't go into all of those, but I'm going to tell you briefly about propensity score matching and maybe regression discontinuity designs. So the basic idea here is that we replace a collection of confounding covariates with one function called the propensity score. And then that's used as if there were only one covariate instead of a whole bunch of them, and we match people on that one covariate that's really a composite. We can get this, we can get a propensity score, it's a probability between 0 and 1, that a person would be assigned to a treatment group. You can get it using logistic regression, especially multivariate logistic regression. It's the conditional probability of that person being assigned to receive the treatment based on their scores on the observed covariates. From a counterfactual perspective, it describes the probability that an individual would have been treated based on their background characteristics.
If there were random assignment.
If there had been random assignment, what you're really doing here is you're constructing a control group after the fact, based on people's scores on covariant variables that are potential confounders. It's a very useful thing to do if you've got the information to do it. And it reduces that selection bias and allows you to get estimates of both of those treatment effects we talked about. A year ago, one of our students in the EIME program did her dissertation on this. It's now being published in Harvard Ed Review.
You have to have a much larger pool of,
It certainly helps.
because it seems like you might,
You not only have to have a large pool, but you need a large number of covariates to select from. So you need background characteristics on those.
So the propensity score matching, like, when you actually get down to the details, is do you look at two individuals who have equal propensity scores, but one of them actually did receive the treatment and the other one didn't, and then you just compare it? And that's like, then you take the average of all those, and that's like what you infer as the treatment
There are
effect?
different ways of doing the matching, but it eventually involves matching them on their propensity score, where their propensity score is a composite of their background characteristics on many variables, and it's reduced to a single probability between 0 and 1. And you do it in R.
How would that work though for like, imagine like you have a 95% probability of being assigned to the treatment group. Like there may be no one in the sample who had that propensity score but did not receive the treatment.
Well, you'd have to have a large group to do that.
that's the question I was really trying
You've
to
got to
get
have
at.
other similar people to do that.
Because if you don't have a large enough pool, you might not actually be able to do it.
Yeah, that's
Because you
true.
wouldn't have, of course.
Propensity score matching is not a panacea. It's a useful tool. It does have some assumptions behind it. You've got to have a large enough group and you've got to have known measures on their covariance. The regression discontinuity design, by the way, you can strike out that word right
Can I
there.
ask a quick question? If there's not a match, if you don't have, you have a lot of people that drop out of your system because there's not a matching propensity score. So that's why you'd have to have a large pool, because there are many who wouldn't have the match and so would end up dropping out. And
There are
not-
different ways of doing the matching and they account for some of them, but that is a problem. Right now, the regression discontinuity design, I'm going to skip over some of these. Please note that some people believe it's the next best to a randomized experiment. It does have strong internal validity. And it's similar to a pretest post-test, but it differs in the way you assign people to the treatment and control. That one is out of place, the one just before this. I'm going to skip down to, here's a regression discontinuity with no effect. So it could be either way. Either these are the people in the treatment group, or these are the people in the control. Or it could be exactly the opposite in this case. Here's an example of one where there was an effect. That effect is measured by this difference right here. Now, here, you're not randomly assigning people. You can assign them on basis of need. For example, everybody who is above a cut score doesn't need to take remedial algebra. I mean, they need remedial algebra. So you put them in the treatment group, and everybody who's above that cut score would be over here. So these groups are known not to be equivalent. But it also solves the problem. You can give the treatment to the people who need the treatment. And then you really focus on measuring right in this area and look at the size of that discrepancy. Now, in this case, it looks like you have to have a linear relationship between this variable and that one. That need to be the case. It could be curvilinear, could be quadratic. It does assume that you use the right regression form. to do it. But you look for a discrepancy, which is either a change in this mean right here, or it could be a change in the slope due to an interaction. It's a very useful design, even though Campbell proposed it 50 years ago. What did I do wrong?
It's funny where you ended it if you wouldn't have said 50 years ago.
He proposed it 50 years ago, but it wasn't widely used until about 20 years ago. And it was the econometricians who basically popularized it. Now it's fairly widely used in education.
So in order to find that discontinuity, do you have to do successive tests at various,
No.
or
This line is placed where your cutoff was for assigning people to the treatment and assigning people to the control. For example, for nearly 10 years now, the Alpine School District, at the end of first grade, has assigned kids who weren't doing well in reading to take a summer reading program, 3-week program. They collected data for 8 or 9 years, but never analyzed it, because they didn't know how to do it, and they didn't have the personnel to do it. One of our doctoral students a year ago addressed it. The problem was, this design assumes that you have a strictly adhered to cutoff. Kids who have scores below such a level, such and such a point on the reading test, take it, and kids who are above that don't take it. Well, we thought this was a good design to use, because they told us that's the way it was implemented. Turned out, they had a lot of kids who were supposed to take the reading, whose family had planned to go to Disneyland, or they had a family reunion or something, and they couldn't be there for those 3 weeks. And they had other kids up here who weren't supposed to take it, who were down here taking it. So we had to use some other analytical procedures that weren't as good as this one. But this is a very good way to go if you have a strict cutoff. Now, in the last 20 years, some creative statisticians and researchers have designed what they call a fuzzy regression, called discontinuity design, that allows you to deal with those issues. But it's better if you don't have to worry about the fuzzy design.
If there's not a discontinuity, then this
Then there's no effect.
design,
Look, the discontinuity is this.
right,
This is the cutoff. So you look for a discontinuity at the cutoff. And if there's not a discontinuity, there's no effect.
so is the way this would be used is they give a test or whatever to the whole population. They look to see if there's discontinuity. If there is a discontinuity, that's
You
how they
don't look
decide.
for the discontinuity until after the treatment. You assign people based on some pre-measure called the assignment variable. Then you give the treatment. Then you look for the discontinuity between the two groups. Does that make sense? Here's some examples of studies that have done it. Yeah, I gotta close this up.
So, Rich, would this kind of bias the findings though? Because, and I'm sure not, but maybe you can help me understand why not. Because if you're using like an assignment score, like a pretest score, and then so you use that to push people into a treatment group that need the treatment, so they're the low achievers. And wouldn't you then, I mean, wasn't that kind of, wouldn't you assume then at the end that that group will be lower than the original group because?
So you don't use a pretest.
let's,
That would make you susceptible. Now, look, I want to wrap this up with one thing. Number one, there's no design that's perfect. They all have their problems. Even though you can't get conclusive answers, you can get defensible answers, and you can ask more informed questions as a result. Now, I would say one other thing. We do teach a course in this. It's in the fall. It's IP&T 674. It's called Quasi-Experimental Design, and it draws from the Campbell approach, the Rubin approach, and the econometrician approach. Thank you.
Thank you, Richard.